Right, welcome back. We're now going to be taking a look at the development of a simulator. And we've been hearing from 3 of the people who've been involved in that process. So just allow me to bring everybody to the stage. Welcome. Thank you for joining AMAHealthcare. I will turn the session over to you now, and I'll be back to handle any Q&A later. So please take it away.
All right, thank you. Hi, everyone. I will just share my screen first. Sure. Okay, should be all right. So hi, everyone. I'm Mael. First of all, I would like to thank Michael and the whole VPA team for hosting this great event and for letting us show what we do. I would also like to thank people who joined me as well. Juliette, which is the R&D head engineer at Prime 3D. It's like the additive manufacturing platform of Paris public hospitals. And I would like to thank also François, which is Paris Cité University full professor and ENT surgeon at Necker, Paris Hospital as well. And finally, I'm Mael, head engineer at MedPrint. Just to give you a little bit more context about what we do at MedPrint, it's a company based in France, specializing in additive manufacturing with a focus on healthcare and medical field. We develop functional models that mimics biomechanical behaviors of tissues like bones, soft tissues, etc. And we also develop full color customized models thanks to different additive manufacturing technology. But as you know, nowadays practitioners need to continue to train throughout their whole career. But how do they train? With what tools? And there are many challenges. And there is one rule, which is never the first time on a patient. And as you guys know, it's very expensive to train in an operating room. There are costs and risks associated with mentored training in the operating room due to longer anesthesia time, for example, during the surgery. And on the other hand, there are many ethical concerns when working with cadavers. By the way, specific pathologies or young cadavers are extremely difficult to find, which is nice. The average cadaver age is about like 70 years old, so we're doing good. That's great. But like, what simulation tools are available for professionals? Do they have realistic haptic feedbacks or not? And do they use procedural simulation tool in a realistic environment? To train, healthcare professionals have access to tools that are more or less realistic, sometimes very expensive, and also subject to significant ethical and regulatory constraints. To give you a little bit more context, I will let François, which uses those tools every day, explain the pros and cons of each of them.
Thank you, Mael. So I'm an ENT surgeon and a professor. So one of my day-to-day issues is how to best teach the residents, and also how to teach continuous surgery for people who are already experts but who want to build on new techniques. So we talked about this with Mael presenting. I think the most important thing to understand in surgery is that we are learning a trade. Okay, we're not learning some things by heart or to answer a test. We're learning how to do something. And so the key part in this is going to be surgical mentorship. It's been so for many years now, at least 100, 200 years. That's how you learn. That's how you learn things. And I wanted to comment on also the sentence, never the first time on the patient. It's of course much more complicated like that, because there are many first times. What is said, never the first time on the patient, is okay, you don't want to do the first time you did a procedure on the patient, you want to do it on the simulator before, okay, but then the first time you're doing a procedure with your mentor, that's still going to be the first time on the patient. The first time you do it on your own, that's still going to be the first time on the patient. And as you progress, you'll be doing first times continuously. So there are multiple first times. And I think that all these other solutions here, which are simulators, I'm going to discuss them in very, very briefly. They have their role at many different steps. Okay, it's not just, okay, let's do some simulation, then you can go to the theater. It's every single step you can offer some simulation to increase your skills and to increase your self-confidence and to be able to go up the ladder and up the surgical stairs, you could say. So the main issue with surgical mentorship, and why don't we just count on surgical mentorship, is that it's not very cost effective and there's lack of availability. Okay, the ideal mentorship is one-on-one, and you can't have one surgeon for every student or apprentice. Okay, so there's an issue of availability also. For years, we've been able to complement surgical mentorship with human cadavers, and that's been fine. The two main limits, and this is even the more so nowadays, will be an ethical limit, because in certain countries, like in France, you can't separate the head from the body or body parts for ethical reasons. And you can have a risk also when you're operating on human cadavers. And the main issue when you're learning to teach diseases is that the cadaver doesn't have a disease. Okay, you're going to reproduce normal anatomy. So that's definitely a limit. Then you have animal models. Those can be used in live procedures. That's clearly something that's very interesting, but of course you'll have very different anatomy and again, no disease model. Okay, so you'll also have limits from that side. And of course, ethically, it's also more and more difficult, like in research, to use animal models. Then you have virtual reality or augmented reality. That can be very interesting from a reproducibility point of view. People can do the thing over and over and over again, but then it will lack tactical feedback. And if you do implement tactical feedback, so you can add haptic feedback to virtual reality, it will still be very much limited to what you're trying to show. And as soon as you want to go out of that zone of comfort, it will be difficult. And so I'd say virtual reality is quite good for beginners, but then as soon as you have a bit of personal experience, it's not really up to the mark. And then the catalog models will be all the simulators out there, which are produced by big companies. And again, I'd say it's the same type of limits as virtual reality, where you'll be, it's quite good for beginners, but then you'll very quickly be closed in to that ecosystem and you won't be able to go out of it. So 3D printing really offers this variability. It offers the diseases and it also offers cost-effective solutions. So I'll hand back to Maël.
So today, as you see, we can meet this. We can meet this kind of meat thanks to additive manufacturing, and we're able to use those technology to have like a better CSR approach with more customizable models with specific pathology. And as you can see on the right-hand side of your screen, we are mixing technologies by taking pros and cons of each of them to produce models with a better cost control and easier logistic and a reduced delay. For example, like the top end of the skull is printed with an FFF printer, pretty classic printer, which produced low-cost part with large build volume. It's pretty easy to use, very convenient. Whereas the bottom end is printed with PolyJet, allowing us to use more expensive technology only on useful areas where we can design soft tissues, bone, etc. To give you an accurate example, it was with this mindset that we developed altogether OTOSURG, a procedural simulator, in collaboration with Dr. Simon and the Prime 3D platform from Paris Hospital. I will let Francois explain his needs on this case and how we use those technologies to answer his needs.
Thank you. So yeah, this is again, I'm an ENT and I specialize in otology. So this is really a case study of the different possibilities of 3D printing applied to this type of procedure. So this is a simulator which reproduces surgery through the ear canal. Conversely to other techniques where we do incisions behind the ear or over the ear, this focuses on trans-canal surgery. To do this type of surgery, we sometimes use a microscope, and that can be used with the simulator. But for now, the past 10 years, we've been using endoscopes. So it's like a telescope that you put directly in the canal, and you can get very close to what you're operating. And that's a completely new skill set. And that was the basis of this simulator. It was that we have on one side residents, so they're sort of discovering the entire otologic surgery. So they're a bit naive of one technique or the other, but they need something to learn on. But also experts. And you have some people who have 20 years of experience in otology with the microscope, and they still have to learn how to switch to the endoscope. And so these very experienced surgeons also need to be able to work on the simulator. So these are two examples here. I use it for residents. Sometimes I use it between cases. This is an example between cases in the operating theater, just above there. I find it quite nice if we've done something on the patient, for example, and the resident hasn't done it before and saw me do it, then the resident can do it on the simulator between cases. That's one application. And just below, this is a collaboration that we've developed with Toronto University, where all the Canadian residents go to Toronto for their otology course, and they use the simulator also in that case to learn the basic procedures. So it's a good combination because as you can see on the left here, for continuous training, we've set up also a course where we use the best of both worlds in my perspective. There's a whole day on the simulator, and so that way they can do at least 6 to 8 cases in the day, which is not possible on a cadaveric model, because you'd have to have 10 heads or something. And so they do different diseases. They train. That means they know where to do the incision. They learn the different steps. And then the next day, we use the cadaveric subject, which still, of course, has a more lifelike perspective, which is normal anatomy. But then they take greater benefit of the cadaveric use also, because they've had the training on the previous day on the simulator. They know exactly what they need to do. They've already gained considerable experience and confidence on that first day, and then they take all they can out of the cadaveric subject there. Then for effective, because compared to experts, they don't know what to do. So if you put them on a cadaveric subject or other thing, they can just completely destroy the model because they've got no idea what they're supposed to do. And so it's also a great way to have trial and error, where you can show them on the simple model. Sometimes you can choose to print a simpler cartridge with colors, for example, which are non-physiological, but you want them to see something specific. So you can decide, okay, I'm going to print this anatomical structure in bright green because I want them to see it and know exactly where it is. There you can do it very easily with the printer. And again, in combination with mentorship, include that simulator to your needs. And that's also a great strength of 3D printing, is that you can tailor very specifically to what you want to teach to that person. You can tailor the best simulator and the best cartridge to that person. Again, I gave the example of a color to show an anatomical structure. But you can also decide, sometimes I don't print the tympanic membrane. Okay, usually when you operate the ear, you have the tympanic membrane. You have to elevate that and then access to other structures. So I can choose for residents, for example, not to print that. And they have direct access to the ossicles behind the tympanic membrane. And so that reduces what they've got to think about. Okay, so I'm just teaching a specific stage of the procedure, for example. And so that's very easy to do with 3D printing. And my last point is very, very important in surgical training. It's validation of surgical competency, because something with 3D printing, sometimes it's seen a bit as a toy. Okay, it's fun. Everybody's very happy to have something 3D printed. It's nice. But you really need to structure the teaching, and validated surgical competency evaluations, which are the OSATs. OSATs is objective, structured technical scores. It's something that's validated, where you can assess every step of the procedure on the simulator, and that way you have you know exactly what you're teaching them, and at the end of the day, you know what you've taught them also, and so they can use that and validate that day of teaching with the simulator. The last point I put is self-confidence. It's also something that we assess in these courses, because it's not just the competency. And here I come back to the sentence, never the first time on the patient. What changes when you've done it on the simulator before? It's not just that you know you have better skills, but it's also you know what your limits are. You have self-confidence in what you're able to do and what you're not able to do. And that also is a very, very important aspect for the patient when you start for the first time on the patient. Yeah, next slide. So this is a brief video you can play. Yeah, thanks. This was a great addition that we had actually. We add, so this is a tympanic perforation. You can see the hole there in the eardrum. It's adding fake blood. So it's blood from theater. It's theater blood. It's not any special blood. It's just theater blood. And so it changes the texture. So it's much more lifelike. And it also the flaps and the different anatomical structures can stick to each other like in a real surgery. And again, this is a difficulty when you have bleeding in these cases. So when they're beginners, you can put just a little bit of blood. If you want to simulate a very bloody surgery, which is again real life, it can happen. You can add more blood and make it more realistic or more complicated, and adjust this to the cases. So maybe we can move on to the next signet. Yeah. So this, for example, in this example, we're elevating the eardrum here, and we're accessing to the structures behind the ear, and there you can see the ossicles. And so we're just going to move them a little bit. That's the chorda. So you can print, of course, with PolyJet the bone, but that's been printed for ages with different techniques, but also the soft tissues. And that's really innovation. That's very, very interesting for these different procedures. Okay, well, I think that's enough for the video. I, of course, share this video if anybody's interested. We can switch to the next slide, please.
Yeah.
And so this was one example of a tympanic perforation. And of course, as I've explained already, one of the great advantages is that these cartridges can come in different diseases and in one given disease in different variants. Okay, in that case, it was a posterior perforation, but you can very easily create an anterior perforation, total perforation. You can fix ossicles to mimic otosclerosis. You can make them move. You can take them out so that the student puts a prosthesis in. You can put a disease inside with skin. You can, I mean, imagination is your limit, and you can really imagine. For the moment, we're building a sort of a catalog, but you can imagine also that at some point it would be very easily for someone who wants to buy cartridges with a specific need. Like, I have these students, I want to teach this specific type of disease to them, that they order a little tweak in the cartridge, and you can easily adapt it to their needs. That's also a great plus. Next slide. I think I've finished. Oh yeah, no, that was the last point. So the last point in this is these are 3 photos of various setups from left to right. In the left, it's in one of my friends in Toronto, Adrian James, in his office. So we were able to test the simulator in his office. The one in the middle is in a medical conference. So it's also something you can very easily use to showcase technology. In this case, there was a robot. So it's not so much about teaching surgery, it's showing what the robot can do in a lifelike situation. And then on the right, that was in a dry lab teaching session. So all of these things that you can't do on a cadaver or on an animal, where you need specific wet lab situations, that's also, I think, a great advantage of this 3D printed technology. I'll hand it back to you, Mel.
Thanks, François. So yes, we work together on the development of OTOSURG. So how it works. The first step was the analysis of the requirements. François explains me its need and the training objective and which surgical gesture he wanted to do on the simulators. It was like cutting skin or drilling bone. And for that, I also had the opportunity to go to the surgery room and to cadaver lessons. And it was very helpful to understand the step of the surgery, all the steps of the surgery. We also talk of the global design of the model. Should it be modular, reusable, or single use? And thanks to all this information, I start to think about the manufacturing method and the 3D printing material available. We also discuss about the production constraints. The main question was, will we be able to reproduce fidelly this complex anatomy? So after that, we were able to start the design of the model with the segmentation part. So we can go on the next slide. So from a CT scan, which is a stack of body images in the 3 directions of space, we were able to extract anatomy like bone or skin. So for that, we use an open source software, which is 3D Slicer. Then we went on the design part. So we perform the design on the open source software Blender. So this part consists mainly in create elements which were not visible on the medical imaging. So for example, ligaments, to adapt segmented structures to production constraints. For example, the ossicles were very, very thin. So we inflate them a little bit to be able to 3D print them. We design also the model with a base and an interchangeable cartridge. And we develop the functional feature of the model to be able to simulate procedure. For example, we wanted to detach the skin from the bone. And for that, we had to make specific design. So we make some iteration of the design according to François' expertise. And after all this part, we had a full virtually model and printable model. So we go on the 3D printing part. So for the 3D printing part on next slide, we decide to use a polyjet technology. So as François said, we use this technology because we can reproduce soft and hard tissue in the same model. And this is very important for the simulation. Then after the 3D printing, we had our first model and we start to iterate on the model, to test the model and to iterate. So we first start with unit tests and simplified geometry to be able to choose the good material. We also test the production limits to assess feasibility and constraints. And we finally add our full first model 3D printing and we iterate on it. We iterate at least, I will say, 5 times. And after that, we add our first model. So the model that François present. So all this process took around 1 year of work. About 1 year. So then François said the validation was very important. So he conducted with his team a study to validate the model with a larger panel of experts and students. The paper is published on Ontology and Neurology review. This gives a great credibility to our model. And now MedPrint commercialize the model. On the next slide, which is its expertise, MedPrint bring a nice packaging to the model, a large-scale production, and a worldwide distribution. Until now, the model is used in Europe, Canada, and US. And it's very important to underline that the collaboration between the 3 of us is very important since, thanks to customer feedbacks, the model is continuously improved. To finish, I wanted to talk about the key benefits of the collaboration. So first, between doctors and engineers. Thanks to our collaboration, we combine medical and technical expertise to drive simulation innovation. The design was based on real clinical needs, and thanks to our proximity, we were able to perform rapid iteration, which was essential for the development. And I will let Maël talk about the collaboration between APHP and MedPrint.
Yeah, so by doing so with this kind of collaboration, it allows us to enhance clinical credibility. We also keep improving product relevance and performance by keeping co-developing models all together with our own skills and our own expertise. And we also try to increase product visibility as much as we can, thanks to commercial power of companies. And thanks to this collaboration, we are scaling up projects like that, and this product, as Juliette said, is now sold worldwide in Canada, EMEA, and etc. So yeah, that's a beautiful story of OTOSURG, and I hope you enjoyed. I hope it allows you to understand a little bit more what we're capable of with new additive manufacturing technologies. And it allows us to have a very large, like nowadays, it allows us to have a very large scope of application between transforming your patient-specific imaging into functional models that mimics the biomechanical behaviors of tissues, or full color models, or customizable demonstration models to showcase your medical devices. There is a very large scope of things that we can do by mixing different additive manufacturing technologies. And so, yeah, if you have any question, feel free to drop it in the chat section, or feel free to join us at the table at our networking session at the end of the day. And again, thanks, Michael. Thanks the OTOSURG team for inviting us.
Oh, thank you for a sort of fascinating look, and congratulations on bringing this product to the sort of commercial sort of state as well. It was really interesting to hear you talking about the sort of blending of various additive manufacturing technologies. And this is probably a question either for you, Michael, or Juliette. What would you like to see those technology providers, the manufacturers of machines and materials in their industry, what do you want to see from them in the future? Is it lower costs, increased reliability, a broader palette? What would you like to come up next?
I mean, most of the time when you work with like very high-end technologies like PolyJet, it's pretty closed, right? So you have to use strategic slicer, you have to use strategic material, and sometimes, for example, on PolyJet, you have like DAP, which is digital anatomy processor or something like that, which allow you to create your own materials, right? You can mix different resin to create your own materials. And I would love for the software to be a little bit more open, to allow us to create more things, because today I find some limitation in these kind of things. And obviously there is a big gap between technologies in terms of cost. Like FFF printer is pretty cheap, right? You can do many things with it. You can have rough surfaces, but hey, like it's pretty cheap, low cost, that's nice. And on the opposite is PolyJet, which is very expensive, and you try to use it only on the area of interest, the area that you're gonna drill, cut, and etc.
This is a question really for Francois. You were talking there about the trainees at the University of Toronto and how they can now perform 6 to 8 simulations per day. What kind of increase in the opportunity to practice those hands-on skills is that compared to the previous training options?
Well, if you use a cadaveric model, often you'll have one head. I mean, concentrating on ear, of course, which is my field, but you'll have one head, so you'll have 2 ears. For ethical and economic reasons, you can't expect to have dozens of heads available for the students. Actually, in Toronto, they developed a while back now also an animal model with sheep heads, and which is quite good because it's very cheap. You can just buy it at the butcher's, really, but with different anatomy. So the limits were that, okay, you need to have the insight to transpose what you've learnt to the patient afterwards. So those, I think, are the main limits. And then again, the big difference is working on diseases. You want to make them train and again then assess them on treating a specific disease, which you can't do with any of the other models.
Oh, wow. Oh, thank you. Thank you all for coming today to share sort of insights, and certainly look forward to seeing what's next as well. So hopefully you'll be able to sort of join us again for the next edition. We've got another session sort of about to start now, so please don't go anywhere. Thank you again to Marc, Juliette, and Francois.
Thank you very much.
Thank you very much, guys. Thank you.
Very much.
Well, we are about